Welcome back to the Deep Dive. We are digging into the latest update for the V-Engine project today, specifically looking at Milestone 7. And I have to be honest, when I first opened the changelog, my eyes sort of glazed over. It's a lot of, well, it just looks like housekeeping.
It really does look that way on the surface. But if you dig a little deeper, M7 is, I think, one of the most significant updates we've seen yet.
See, that's what I'm trying to wrap my head around. I see lists of bug fixes, I see refactoring, I see cleanup. It feels like the team spent a month just tidying up.
Yeah.
But the summary calls this the vertical slice milestone. That sounds like a big deal. So why is this update heavier than it looks?
Because, you can't build a skyscraper on a swamp, and Milestone 7 M7 was all about draining that swamp.
Draining the swamp, okay.
The team calls it greenboard status. They have 319 unit tests, 119 integration tests, and this is the big one, 2,402 assertions, and every single one is passing.
2,000 assertions. I mean, I get what a test is, but an assertion is like a tripwire in the code.
That's a perfect analogy. An assertion is a line of code that just says, hey, if this variable isn't exactly what I expect it to be, stop the engine. Immediately.
Because something is fundamentally broken.
Exactly. So to have over 2,400 of those tripwires active and not a single one of them tripping, that means the engine isn't just working anymore. It's stable. It's predictable.
Okay, so they built a rock-solid foundation. Let's talk about what they actually built on top of it then. You mentioned the term vertical slice. My understanding of that in game dev is like a sliver of the game that has everything working, audio, AI, physics, all at once.
Precisely. Before M7, the V-engine was more like a collection of parts. You had a physics engine over here that could move boxes, an audio engine over there that could play files. But they didn't really know about each other. M7 was about forcing them to talk.
Okay, let's start with audio then, because looking at the notes, it seems like they did way more than just play a sound.
They really did. I mean, phase one was completing the backend WinMM for Windows, ALSA for Linux. But the really interesting part is the spatialization.
Spatialization. So making sure the sound comes from the right place in 3D space.
It's that, but it's also the attenuation. You know how volume drops off over distance. They implemented stereo panning, different distance models. If a sound source is to your left, you hear it in your left ear. If it's 50 meters away, it's quieter.
That seems pretty standard for a game engine, though, doesn't it?
For a commercial one, like Unity or Unreal, sure. But remember, they're building this from scratch, getting the math right so a sound pans smoothly as you walk past it without any popping or clicking. That's surprisingly hard. And they didn't stop there. They integrated it with physics for occlusion.
Physics occlusion. So like, if I'm standing behind a wall, the sound is muffled.
That's the idea. Before playing a sound, the audio system literally asks the physics system, hey, is there a solid object between the listener and this noise? And if the answer is yes, it'll change the volume and properties of the sound.
That's cool, but doesn't that add a ton of processing overhead? I mean, physics checks aren't free.
It does add cost, and that's why the Polish part of this milestone matters so much. They implemented something called VPAC, audio asset packaging, using ZISTD compression.
ZIST. Is that a file format?
It's a compression algorithm. See, audio files are huge. They're often the biggest part of a game's download. If you don't compress them, you run out of RAM. If you compress them too much, the CPU just chokes trying to play them. ZISTD is a sweet spot, high compression, but very fast decompression. It's one of those unsexy behind-the-scenes features, but without it, that cool occlusion system would probably grind the game to a halt.
So the engine is getting smarter about resources.
Yeah.
Speaking of smart, let's pivot to the AI, because there's a phrase in the notes here that sounds like a complete oxymoron to me. Deterministic PCG-RNG.
It does sound contradictory, doesn't it?
A random number generator implies it's random. Deterministic implies it's predictable. How can you have a predictable random number?
Okay, think about it from a developer's perspective. You're testing the game. An enemy AI runs into a wall and gets stuck. You stop the game, you change a line of code, and you hit play again to see if you fixed it. But this time, because the RNG is truly random, the enemy decides to walk the other way.
Oh, that would be infuriating. You can't reproduce the bug.
It's a complete nightmare. So a deterministic RNG just means you can seed the generator with a specific number, let's say 1234, and it will produce the exact same sequence of random numbers every single time. It lets you replay chaos.
So it feels random to the player, but the developer actually controls the timeline.
Correct. And they plug this new predictable brain into the audio system we were just talking about. They call it sensory integration.
Is this the whole hearing footsteps thing?
Yes. They added a sound stimulus event. If the player moves, the physics system calculates the footstep. The audio system plays the sound, and it broadcasts an event. The AI receives that event and updates its behavior tree.
So the AI isn't cheating. It doesn't just read my character's X and Y coordinates.
No, it has to actually hear that event.
Hmm.
If you're sneaking and you don't trigger a sound event, the AI just stays in its patrol state. But if you run, it gets that stimulus and switches to investigate.
That really drives home that whole vertical slice idea. Physics triggers audio, and audio triggers AI. It's a closed loop.
It is. And to make all that logic run smoothly, they had to do some serious house cleaning on the code itself. Which brings us to the part that might have bored you at first, the main.cpp refactor.
Yeah, I saw that. They cut the main file from over 1,000 lines to just 300. I assume they just, deleted some old features.
No, they actually added features, but they organized the mess. In early development, main.cpp always becomes this junk drawer. You need to test something, throw it in main, need to initialize a system, put it in main.
And eventually you can't find anything.
Right. It becomes spaghetti code. M7 was about taking that junk drawer and properly organizing it. They moved all the demo logic to its own files, scene flow to handlers. A 70% reduction in that entry point code means the architecture is finally mature. It's modular.
It sounds like they're preparing for bigger things, which I guess leads me to the compute system. I'm seeing mentions of shader GAC and hot reloading. Why is that important right now?
Because we're getting to the limits of what a CPU can do alone. Modern engines offload heavy math-like particle simulations or huge physics calculations to the GPU. But managing that is hard. So M7 introduces the compute system infrastructure, and Shader lets them compile those GPU programs while the game is running.
So if I'm a graphics programmer, I can tweak a particle effect and see the change instantly without having to restart the entire engine.
Exactly. It speeds up iteration time massively. And they're going to need that speed because the biggest chunk of work in M7 was all about physics.
Ah, the physics, the meat of the update. I was reading through the bug reports, and it really sounds like they were fighting a war against jitter.
Jitter is the silent killer of physics engines.
It sounds funny, though, like the cubes had too much coffee.
It looks funny until you try to stack 10 boxes and the whole tower just collapses because the bottom box is vibrating for no reason. This happens because of tiny errors in floating point math. The computer can't always represent 0 perfectly, so it thinks the box is still moving, just a tiny bit.
So how do they fix it? I see they overhauled the sleep system.
Putting objects to sleep is the standard solution. If a box hasn't moved much in a few frames, you tell the physics engine, stop calculating this, it's a statue now. The problem was the rules for when to sleep were just too complex.
They had sleep gates.
Yeah, like 5 or 6 different checks. Is it touching the ground? Is the velocity low enough? Is the angular velocity low enough? It was too sensitive. Things would wake up when they really shouldn't. So they simplified the rules down to just 2 or 3 hard conditions. But the real game changer was island stabilization.
Okay, explain islands to me, because I'm picturing palm trees, and I don't think that's right.
In physics terms, an island is a group of objects that are all touching each other. So a stack of crates is an island. The new system looks at the group as a whole. It says, okay, the bottom crate is a little jittery, but the top crate is still, and the neighbor is still. Let's just force the whole group to sleep.
It's like peer pressure for physics objects. Everyone else is sleeping, so you should too.
That's a perfect way to describe it, actually. It stops one bad apple from keeping the whole stack awake and burning CPU cycles. And for the objects that refuse to listen, they added the floating cube fix.
This was my favorite part of the notes. It seemed remarkably pragmatic.
It's a total sledgehammer. They added logic that just tracks how long an object has been hovering without a collision. If a cube has been floating for 300 frames, about 5 seconds, and it has very low velocity, the engine just assumes it's a bug and either forces it to sleep or just destroys it.
You have been hovering for 5 seconds. You are clearly broken. Goodbye.
Sometimes engineering is about elegance, and sometimes it's about just making the problem go away. And it worked. They have Tier 2 integration tests now that prove a stack of cubes will settle down and go to sleep within 60 seconds every time.
Stability is great, but we also need speed. And this is where the conversation gets a little dense for me. The job system and the parallelization migration.
This is the architectural backbone of the entire engine.
So explain the before and after for me.
Before M7, the physics ran serially. Imagine a grocery store with only one checkout lane open. It doesn't matter how many customers you have. They all have to go through that one cashier.
And that cashier is the main CPU thread.
Right, and our modern CPUs have 8, 12, 16 cores. Most of them are just sitting there, idle. M7 implemented Tier 4 parallelization. They basically opened up all the checkout lanes.
So they split the work up.
Yes, specifically for things like broad phase and narrow phase collision detection. The engine takes the world, divides it into a grid, and assigns different grid cells to different worker threads. But you can't just run everything all at once because some tasks depend on others.
You can't bag the groceries until you've scanned them.
Exactly. And to manage that dependency, they built the physics job graph. It's a directed acyclic graph, or DAG.
A DAG. Okay, I've heard the term, but make it real for me.
Think of it like a recipe. The engine looks at all the physics tasks for the frame. It sees that update positions depends on check collisions, but maybe update particle effects doesn't depend on either of those, so it builds this graph of dependencies.
And then it just floods the system with work.
It looks for any task that has its dependencies met and fires it off to the first available CPU core. It ensures that no core is ever waiting if there's work that could be done.
That sounds incredibly efficient, but also dangerously complex.
It is, but it's necessary. Because M7 was really just the setup. Milestone 8, based on the roadmap in PLAN.md, is where they're going to push this whole system to its limit.
Before we jump to M8, there were a few production features in M7 that I think players will actually notice, specifically the Steam integration.
Yes. And they didn't just add the overlay, they added the full Steam input API. So you get proper controller support, haptics, action sets, and Steam Cloud support.
And I saw a note about conflict resolution for cloud saves.
That sounds tricky.
It's one of those things you don't think about until it breaks. You play on your PC, then you go play on your Steam Deck, which save file is the real one.
Yeah.
They implemented timestamp comparison to handle that. So if the files conflict, the system knows how to ask the user or just resolve it automatically.
And for the developers listening, there was a workflow tweak with the VPAC system.
Loose file detection.
Yeah.
We talked about those compressed VPAC files earlier. They're great for shipping the game, but they're terrible for development. You don't want to repack the whole game just because you changed one texture. So this lets the engine ignore the packed file if it sees a loose, newer version on the hard drive.
Correct. It prioritizes the raw file on your disk. It means devs can iterate instantly, but the game is still ready to ship at a moment's notice.
Smart. Okay, let's shift gears. M7 is done. The board is green. The swamp is drained. Now we look at the roadmap for Milestone 8. What's the headline for M8?
If M7 was about stability, M8 is all about speed. The theme is the jobified pipeline.
We just talked about the job graph. Isn't that already done?
They built the capability for it, the infrastructure. Now they're going to move the entire physics loop inside it. In M7, the fixed update loop, the heartbeat of the physics engine, was still kind of managing things from the top down. In M8, they want to break that entire loop into individual jobs.
So literally everything becomes a node in that graph we talked about.
Everything. And to make that safe, they're introducing something called graph coloring for the constraint solver.
Okay, graph coloring. I'm picturing a coloring book, and I really don't think that helps. What is the problem they're trying to solve here?
The problem is race conditions. Imagine two worker threads are running at the same time. Thread A is trying to move box 1. Thread B is trying to move box 2. But box 1 is resting on top of box 2.
So if they both try to move them at the exact same time...
The physics just explodes. The simulation breaks because they're fighting over the same data. Usually you solve this by just running it all on one thread, but that's slow.
So how does coloring help?
You analyze all the contacts. You say, okay, box 1 and box 2 touch, so they are dangerous neighbors. Let's paint the contact between them red. Then you find another pair of boxes way over on the other side of the room that don't touch the first pair. You can paint them red too.
Ah, so you group the safe, non-conflicting tasks together.
You group the tasks that don't interfere with each other. Then you tell the computer, solve all the red constraints. It can do that in parallel because none of them touch. Then solve all the blue constraints, and so on.
That sounds remarkably clever, but also like a massive headache to implement.
It is extremely difficult. It requires complex graph algorithms just to set up the frame. But if they pull it off, the physics solver becomes exponentially faster.
And they're also talking about a structure of arrays refactor.
That's a memory optimization. So instead of storing an object as a bundle position, rotation, velocity, you store all the positions in one long list, all the velocities in another.
Why does the computer care how it's organized?
Because of the CPU cache.
Hmm.
The CPU absolutely loves reading data in straight lines. If it can chew through 1,000 velocity variables in a row without having to jump all over memory, it runs much, much faster.
It really feels like M8 is just stripping the engine down and tuning it for maximum performance.
And the ultimate goal of M8 seems to be taking that GPU compute system they scaffolded in M7 and finally running the physics on the video card itself.
So bringing it all together, M7 gave us a vertical slice, the code is clean, the systems are talking to each other, and the jitter is gone.
And we have a platform that is production ready. With the Steam integration and all the stable tests, you could technically ship a simple game on this engine today.
But M8 is where they take the safety rails off.
That's the feeling I get. M7 was the necessary, maybe even boring work. M8 is the dangerous, exciting work. They're going to add immense complexity with graph coloring and full jobification.
So here's a question I want to leave everyone with. We've seen engines go down this rabbit hole before. You chase performance, you add complexity, and suddenly the code becomes impossible to read or debug.
It's the classic trade-off.
Can they implement graph coloring and GPU physics without losing the stability they just fought so hard to get in M7? The green board is nice, but will it stay green when you start tearing the solver apart?
That is the question for the next retrospective, I think.
And we will be here to cover it. A huge congrats to the V-Engine team on Milestone 7. It sounds like you've built a beast of a foundation. Now let's see how fast it can run. Thanks for listening to The Deep Dive.
See you next time.